Hello and welcome back. Okay, I am still getting used to not having any breadboards on this build at the moment, but I'll enjoy it while it lasts because I'm going to be adding some functionality soon. I've also tried putting the LCD over here for a while because the work I want to do now is going to involve the address bus, so it's going to be easier to do some breadboards here. Now, a few videos back I built this little circuit which was designed to let me use these bodge connections to fit a RAM chip into this socket. And the idea here is I want to replace this memory module with one that's entirely RAM, but can shadow memory copy the ROM into the RAM. So then we can have some more flexible programs that can work off a larger RAM region. Now, this gets me a RAM in, and then I started work on this little board, which you haven't seen, to allow me to fit a ROM chip on top of that. And all the wiring here was getting quite complex, and I think I even commented in that video that it would be so much easier to have done this as a custom PCB. But at the same time as doing all of that, I was planning out the last of the ALU modules. So when I ordered the ALU result, I spent a quick bit of time designing a PCB to do this job and ordered it at the same time. Let's take a quick look at the designing of that. Okay, so crazy idea. Let's see if I can make a ROM-RAM bodge and tag it on my next order. Right, so I've got 3 copies of the ROM chip here. One is going to have pin headers in to go down into the ZIF socket. One will house the RAM chip and one will house a ROM chip. A chip select we do want to propagate. Now we know in the socket write enable is simply going to be connected to VCC. Which is exactly what we want to do on our ROM chip. Okay, I'm quite keen to see this. So this replaces the combination of these 2 boards. First time I've had something made up in yellow. Let's solder it up and see how it goes. I've got a choice between a vertical one of these or a right angle one. I think the right angle one might be slightly easier for getting connections into the breadboard. I do have to be careful here to make sure I don't block off the terminals I need. So these pins are designed to go down into the ZIF socket, and then we have regular sockets on top that will take the ROM chip and the RAM chip. Which order is it best to do these in? Actually gave me 6 of these. It doesn't quite protrude through enough. And that's slightly too much. Now I think I should be able to get a good solder joint even though I'm only showing the slightest bit through the top. But let's test that theory. Yeah, that's fine. Okay, so that was so completely trivial compared to trying to hack it together with bits of stripboard. Okay, let's get the build back out and have a play with this. Something else I'm interested in doing is writing some code that needs everything to be RAM. Now, I don't want to write a great big piece of test code from scratch, but this Fibonacci sequence code, it uses my display library, and my display library has got some fixed data that go in the ROM, but it's also got this 1 byte of status data for current line, and that gets incremented each time it draws a line, so it knows to clear the screen and go back to the top left when it's completed 4 lines. So I'm just going to change that so that it stays in the lower portion of memory, which is normally ROM. And that means it will start initialized to 0. Can also get rid of these 3 lines of code which are setting the stored value to 0 during initialization. So we have totally broken this now. If we run this code from a ROM chip, it will constantly draw to line 0, the top line, and only when we've made the system work with RAM in the bottom half will this code start working again. Okay, so I'm going to run the Fibonacci ROM as it previously stood. So this will happily switch between lines and work correctly. Let's try this version. It's starting off exactly the same. Okay. I just had to go back and look at the code and see the way I assumed that the first line was going to be drawn immediately after the clear. So that's why it's always drawing on the second line. But this kind of still demonstrates that principle that the variable isn't changed when we write to it, and that's why it's constantly redrawing the same line. Right, so now we've got our module. I should be able to put the ROM chip into the lower space here. These sockets are not designed for repeated insertion and removal. Okay, so we've got socket output enable and connect that direct to ROM output enable. And that's basically making the connection that we broke on the ROM chip. So this should operate as the ROM chip. Okay, so that's working as we'd hoped. I need to reclaim this RAM chip. And now we need to work out the circuit that we plug into here and in these locations to actually handle the copying of the contents of the ROM into the RAM. So let's start to look at that circuit. Okay, so what we want to do here is we want to cycle through all of the addresses covered by the RAM chip and the ROM chip. Then we just need to toggle the appropriate lines to make the ROM chip read and the RAM chip write. And then once that's done, we want to switch into a different state where the ROM chip has nothing to do with it and just the RAM chip is operating as a RAM chip in the way it did with the original circuit we built. So going to need to add some breadboards back to the build. Okay, so this is probably going to be really obvious, but I've got a bunch of these 193 counter chips. These are up-down counters I only actually need the up counting functionality on here, but I've got a whole bunch of these and I pretty much have them memorized now. Now we've only got to cover 15 bits of range, but these are 4 bits a piece, so we're going to use 4 of them. Right, first thing we need to deal with is the clear lines. I'm going to connect all of these together because I imagine we're going to want to use that. Though for now, let's just connect it to ground so it's not clearing. Very similar situation is the parallel load. What's interesting about this one is the parallel load is active low, but the reset is active high. And that might come in handy depending on what signal we've got to clear the settings. I'm just going to pull that high for now though. Now we've got the count up and the count down, and then we've got the carry out and the borrow out. So we can ignore that. The lines we're not using here we're supposed to pull up. I think we can get away without doing that with the LS series on breadboard. We have to remember to do it properly on the PCB. But we want to connect the carry out lines to the count up lines. I remember making a whole bunch of wires this shape when I was doing the counter address registers, but I couldn't find any of them when I went looking. Okay, now what we could really do with is some kind of a clock to count through the addresses. I don't know what I'm going to do on the PCB, but here's a 555 timer. It's a nice easy way of doing it for now. To be careful because the power and ground aren't quite in the same location as they are in a lot of the other chips we deal with. And we connect together the 2 comparator inputs. Get a capacitor between there and ground. We've got the reset line we need. Pull that height. Okay, so there's the output line. Get an LED on that. Okay, I just found this resistor next to that LED, so should be fine. Here's our pull-up that's going to be charging this capacitor. Then on the discharge line, we've got a far lower resistor. So that should be enough to flash. That looks promising. Okay, so let's look at the output. So that's going into the first count up line. So in theory, our counter should be ticking away now. First 2 bits are there. Right, looks like the right binary count pattern. Let's fill the rest in. Trying to get these in the same relative place because it's going to make life a lot easier. That looks right. It does occur to me that it may not matter what order I put these white wires in at all, because as long as it goes through all the permutations, the circuit will work. That doesn't seem right. Everything apart from this chip seems to be working fine. That one's not behaving itself exactly either. Yeah, I think that one's behaving itself now. Maybe I do need the lines pulled up. Now we need some kind of a state for when we're copying and when we're not copying. So I think what I'm going to do is build a set reset latch. So we need to feed output of 1 to the input of another. And do the same the other way. Power and ground. I'm going to steal this LED. Okay, I'm going to pull one of these inputs high. took the LED out, but surely that's not going to have affected it. I took the pull-up out. Okay, which of these was supposed to be that one? Okay, so finally, instead of the carry line daisy chaining to another counter chip, I'm going to put it into the set reset latch. So now when it wraps around and carries, resets the latch back into place. So now let's take this clear line that we pulled low and put that there. That's cool. So now we've got this two-state circuit which will count all the way through the 16-bit range. I keep forgetting these don't stay in properly. Okay, that's pretty cool. Okay, I want the ROM chip to be active for now, and I want the RAM chip to be inactive. So that's output enable on the RAM chip. I'm just going to bring that high because it's active low. Need power for my circuit, and this should work. Now we need to get this address we're generating over here, but we need to do that conditionally because obviously these address lines are directly wired to the bus, and that's going to be a horrible contention issue. Now fortunately there was a little bit of planning ahead for that. Now this line is memory acknowledge. Now the purpose of this line is to signify when an external device or something that isn't the processor can access the memory buses because the CPU is not using it. That line's currently high, which means we can't use it, but every single cycle the CPU is executing, it will be doing something with memory. But I do let that line go low in one specific situation, and that's during a reset. And that sounds like a really good time for us to do that memory copy. So if this line is low, nothing is driving the address bus, it's currently floating, and we can do what we want. So let's get rid of these LEDs. Now I did think about using 541 line drivers for this, but I'm actually going to use 574 latch chips. In the same way we use the 574 latch chips on the output of the address registers. And basically making this work an awful lot like one of the address registers, so we can be very sure things match up. Notice here I'm putting them in upside down, just because it's going to be a lot easier to manage the wiring that way. So that means the ground lines are in the top left. Okay, so these ones are going to be copy, and then these will be output enable. The output enable is going to be our memory acknowledge line. Okay, so I've stepped this out of reset state and now this line is floating. If I reset it and let it step into reset state, then it's no longer floating. So I've wired that up correctly. I'm going to pull that top address line low, just because we don't want to access the other RAM chip. Getting erratic behavior out of here because we're not actually activating the copy line. That's more like it. So now we activate the circuit and we fire through the first 32K addresses twice, because the top bit we're just ignoring. We can not worry about that right now though. And then we let it execute and it's all working. Oh, that's cool. Okay, so now we need to go through these lines and work out the right thing to do. So at the moment the ROM chip is permanently active, and what we want is for when we're not in our memory access state or our memory copy state, we want the RAM chip to be active. And for that we need the memory write line connected to the RAM's write line, which we've accessed here, and we need the ROM chip to have nothing to do with it. So, right, now I think we can cover this quite simply because the output enable line on the ROM chip, we connect that to the acknowledge line, because the only time the acknowledge line runs low is when we're running our system over here, and that's the only time we want the ROM chip to be outputting data. RAM chip's going to be a bit more complex though. So RAM output enable, we can start off by connecting that to the output enable from the socket, which says that the lower 32K of memory needs to output, but we need to do that all times when this line isn't low. I need an inverted form of the acknowledge line, and then I think I should OR that with the socket's output enable. So I've got 74LS32 here, which is for OR gates. So that gives us the RAM output enable. The write enable line for now, we can leave that as high. So ROM output enable, that's low, RAM output enable, it's high. Step until reset is off, ROM output enable, that's low, RAM output enable is high. Address select hadn't changed. ROM output enable is high, RAM output enable is low. Write enable is high. Right, I'm going to get the oscilloscope on. I'm going to look at when some of these lines are changing. Okay, so the clock is constantly running, and I think we need to stop doing that. I'm going to take the reset signal from this 555. Instead of pulling it high, we'll take it from our set reset latch. So now it runs only when we're running. That's good. Now this clock signal is driving the counter, so it's going to be changing, the outputs from the counters are going to change when that line goes high. Then the latches are going to try and pull the data in immediately, and that's a race condition. I think I want to invert that clock. Okay, I'm going to bring in a dedicated inverter. Okay, so if we're going to treat our clock line as the write enable line that goes to the RAM, we need to merge that with the write enable line that's coming from the RAM module with an AND gate. Right, we don't have any AND gates here, but we do have NAND gates. Okay, in theory, I think that's everything. So if I push this button now, it's going to copy the entirety of this ROM chip onto this RAM chip, we hope. So this should be reading from the RAM chip. Okay, but the write operation hasn't worked. Right, it is reading from the RAM chip. Let's try and prove that. We have successfully copied from the ROM chip to the RAM chip. The only thing that's not happening is our write. Yeah, no, I've messed this up, haven't I? RAM write enable is high because I've inverted the clock going into that circuit. Does that mean the write's worked? Yes! Oh, that's awesome. Okay, so the net result of everything we've done today is we've taken it full circle back to where we started with the Fibonacci code working. But what we've got is this circuit here. Let's reset this down. The program code we're running is on this ROM chip here. When I push this button, the contents of this ROM chip is copied to this RAM chip, and then when we execute the code, it runs from the RAM chip in a situation where the entirety of memory is 64 kilobytes of RAM. This is exactly the situation I wanted, the memory architecture that I want to use on the processor going forward. So we've just got flat 64K of RAM, and then we've got this little circuit that copies whatever ROM chip we've got into there. That gives us a lot of extra flexibility going forward. Now what I do want to do is add an additional bit of circuitry to this to make it so we don't need to push this button. I want to handle some reset control logic. So there's a bit of extra complexity there. We also need to add circuitry to hold the main CPU in reset so that it's got time to copy the whole of the chip over. And then I want to design up the PCB, fit all of that into there, and get a new PCB spun up. So we've just got a ROM socket, but instead of running from RAM and ROM, it copies it. I'm really pleased with this though. That's cool. Getting this new RAM system up and running is the big prerequisite I want to get done before I move on to the VGA circuitry, which I know a whole bunch of you are waiting for. So I do hope you found this interesting. I'll see you again soon. Goodbye.